The map is not supposed to attract attention. Small irregularities are expected. A few warmer regions, a few colder ones. Nothing dramatic. Then one region refuses to behave like the rest. On the map, a giant cold region appears. It is not just slightly different from its surroundings. It stands out, larger than expected, colder than expected, visible enough to draw attention in a place where extreme features are not supposed to dominate the landscape. The problem is not simply that a cold patch exists. Random fluctuations should create unusual regions from time to time. The problem is how far this one seems to push beyond what those ordinary fluctuations are expected to produce. Instead of blending into the background, the region keeps pulling attention back toward itself. A map that should represent the universe's earliest conditions now contains a feature that looks increasingly difficult to dismiss as business as usual. The assumption begins to weaken. This no longer feels like an ordinary statistical accident. It starts to look like a physical problem. And if the region is real, something must have created it. The question is, what? Researchers start looking away from the cold spot itself and toward the space in front of it. If the anomaly is only a rare statistical accident, then the search may lead nowhere. The cold region would simply exist, disconnected from anything else that can be observed. But that is not what begins to happen. Researchers compare one map against another. The same patch of sky keeps appearing. A large-scale structure shows up in the direction of the cold spot. So do regions where less matter appears to exist than expected. On maps of the distant universe, the location of these features starts lining up with the location of the cold spot. The alignment does not prove anything. The cold spot remains exactly where it was before. The measurements do not suddenly solve the mystery. What changes is the status of the simplest explanation. The anomaly no longer appears completely isolated. A visible feature on one map now seems connected to something visible on another. The search is no longer looking for an explanation from nowhere. It now has a target. That connection creates pressure. If real structures occupy the same region of the sky, then the cold spot becomes harder to dismiss as nothing more than an unlikely roll of the cosmic dice. The possibility begins to shift. Maybe the anomaly is not standing alone. Maybe something between Earth and the distant universe is involved. And that introduces a new problem. Even if a giant underdense region exists in that direction, can a structure like that actually create an effect large enough to explain what astronomers are seeing? The pieces begin to fit together. A cold region exists on the map of the early universe. In the same direction, astronomers find an enormous, underdense region, a place where matter appears unusually sparse. The next step is obvious. Instead of treating the two observations as separate problems, researchers ask whether one could be creating the other. Or the first time, the anomaly has a workable explanation. Ancient light crosses the universe and enters a vast region containing less matter than expected. By the time that light reaches Earth, it arrives carrying a slightly different energy signature than nearby light that traveled through denser regions. On the map, that difference can appear as a colder patch. For the first time, the cold spot is no longer just an anomaly waiting for an explanation. It has a process attached to it. It has a cause that can be described, tested, and measured. The shift is important. The strange patch on the map starts looking less like a cosmic mistake and more like the visible effect of a real structure sitting between Earth and the distant universe. For a moment, the problem appears close to solved. Maybe nothing extraordinary happened at all. Maybe the cold spot is simply the signature left behind by a giant void along the line of sight. And if that explanation is correct, one prediction follows naturally. The measured properties of the void should be able to reproduce the strength of the cold spot itself. The test seems straightforward. If the cold spot is being created by a giant underdense region, then the numbers should line up. Measure the structure, measure the temperature deficit, compare the two. For a while, the explanation survives because it has something every good explanation needs: a prediction. The void should be large enough, deep enough, and influential enough to create the effect appearing on the map. So researchers keep measuring. They refine the observations. They measure the candidate structures again. Then they place the predicted effect beside the observed cold spot and compare the two. And the confidence begins to drain away. The structures are still there. The cold spot is still there. What starts to change is the relationship between them. The numbers stop lining up. The proposed cause appears weaker than the effect it is supposed to create. The proposed solution does not disappear in a single moment. Instead, it gradually loses the ability to do the job it was supposed to do. The void remains a plausible contributor, but follow-up analyses indicate that the observed structures do not appear sufficient to generate the full temperature deficit seen in the cold spot. That creates a difficult contradiction. The anomaly survives the test. The explanation does not. The observation stays on the map. The certainty does not. The feature on the map remains visible. The evidence for the cold spot is not erased. What weakens is confidence that the largest known candidate cause can fully account for what is being observed. The universe still contains the cold region. What it represents becomes uncertain again. And that may be the most uncomfortable outcome of all. The proposed cause exists. The anomaly exists. Yet the measured cause no longer seems strong enough to produce the measured effect. Decades pass. The cold spot remains on the map. New observations arrive. New analyses are performed. Proposed explanations rise and weaken. Yet the central fact never changes. The unusual cold region is still there, occupying the same place in the sky and demanding the same answer. What changes is the meaning of that persistence. At first, the challenge seems straightforward. Find the cause, and the anomaly becomes part of the normal picture of the universe. But the anomaly outlasts its strongest explanation. As a result, the debate is no longer centered on whether the cold spot exists. The measurements continue to show it. The question is what those measurements mean. One possibility remains that the cold spot is an extraordinarily unlikely fluctuation, a rare outcome that happened to appear in a universe governed by familiar statistical rules. The other possibility is more uncomfortable. The expectations used to predict what large-scale patterns should look like may be incomplete in this particular case. That is why the cold spot still matters decades later. The challenge is no longer finding the anomaly. The anomaly was found long ago. The challenge is deciding what it means. Either an extraordinarily unlikely fluctuation happened exactly where astronomers observed it, or one of the assumptions used to predict what the universe should look like is failing in a place where it was expected to work. The cold spot is not important because it is cold. It is important because prediction and measurement have not fully agreed. And until they do, the map remains a reminder that even the most trusted models are only as strong as the observations that continue to support them.